Any questions about how we got that before we finish this off? All right. Now this is what we want to take a partial derivative of respect to x. So now we'll fill this in. So it's partial respect to x, the integral from x1 to x of p of ty dt. Well, we're taking the derivative of this integral as partial respect to x of an integral with x serving as the upper limit. So we actually apply the other part of the fundamental theorem of calculus, what we don't normally use, that the derivative of this with respect to x is just going to be p of xy. So by defining f in this way and choosing a convenient path, we were able to show, because the path doesn't matter, we were able to show that partial of this f with respect to x is the x component of a vector field. Whereas if you choose a different path, maybe from here to here, to point x, y1, and then integrate along a vertical line segment, you do the same thing and you get partial respect to y of f of xy turns out to be the y component of this vector field. So the gradient of little f turns out to be big F. So f really is conservative. Okay. So as long as you're careful about what kind of domain you're talking about, where the line integral is path independent, as long as the domain doesn't have any holes in it, it actually does go both ways. That we have complete equivalence here. That if a line integral is path independent, then the vector field that you're taking a line integral of is conservative, and vice versa. So here we see how path independence can be exploited to use a path that allows us to easily show that the gradient is what we expect it to be, or hope it'll be. All right. So to summarize, that f is conservative if and only if its line integral is path independent. On a simply connected domain. All right. Now, that's all well and good, but the thing is, we want to be able to evaluate line integrals like this as easily as possible. Now, having this as a starting point, but that's all it is. Because if you're given a vector field and you know it's conservative, well, using a fundamental theorem of line integrals requires using its function little f. And if you define little f in this way, like I did here, as its integral, well, that's not a very convenient way to go to try to evaluate this line integral. If we have formulas for the vector field big F, we need a formula for little f as well. So we need to be able to do that. But before we even start down that road, we have another question to ask. that is given a vector field F, all right, how do we know if it's conservative at all? Because if it's not, then it doesn't do any good to try to evaluate its line integral using the fundamental theorem of line integrals. We just have to do it a more tedious way. All right. So, okay. And you can't very well ask a vector field how it feels about the healthcare bill. So, fortunately, there's a nice simple test that you can use. So 2 dimensions. What? Anyway, so suppose big F is a gradient of some function little f. So that means that fx is equal to p, little f with respect to y is equal to q. All right. Then, let's take this equation, differentiate both sides of it with respect to y. So fxy is equal to py. Let's take this differentiated with respect to x. fyx is equal to qx. So, how does carrying out these particular differentiations help us? Because what do we know about fxy and fyx? They're equal, provided that they're continuous. So these are equal, therefore these should be equal as well. So this is our test. Partial of p with respect to y is equal to partial of q with respect to x. So given any vector field in 2 dimensions, you can, so the vector field of this form, you can just try this, and if it holds, then yes, it's conservative. Therefore, you know that its line integral is going to be path independent. You can use the fundamental theorem of line integrals if you can find the function little f, which we will be able to. But before we take a look at that, what about 3 dimensions? Suppose you have a vector field in 3D space, PQR. How can you tell it is conservative? Okay. Well, if it is, then we have fx is equal to p, fy is equal to q, fz is equal to r. So, how can we use a similar idea to what we saw in 2 dimensions to come up with a test like this in 3 dimensions? How can we use that same kind of approach to smoke out whether this is conservative? So here we just chose our differentiations judiciously, got a situation where we had mixed partials that we needed to be equal, and that's how our test came about. So what's the way to use similar logic in this case? Because Clairaut's theorem still applies if a mixed second partial derivatives being equal.
I don't know, would it help to divide by each side by the function?
No? Alright, so don't do anything that's too different than what we did over here.
Oh.
Alright, so piggyback off of that.